The color rendering index, sometimes called color rendition index, is a quantitative measure of the ability of a light source to reveal the colors of various objects faithfully in comparison with an ideal or natural light source. Light sources with a high CRI are desirable in color-critical applications such as photography and cinematography. It is defined by the International Commission on Illumination as follows. Color rendering, effect of an illuminant on the color appearance of objects by conscious or subconscious comparison with their color appearance under a reference illuminant. The CRI of a light source does not indicate the apparent color of the light source. That information is under the rubric of the correlated color temperature. In the pictures at right it can be noticed that the spectra have different structure, the incandescent lamp gives a continuum, and the fluorescent lamp gives separate lines from the mercury emission. CRI's ability to predict color appearance has been criticized in favor of measures based on color appearance models, such as CIE-CAMO2 and, for daylight simulators, the CIE-metamerism index. CRI is not a good indicator for use in visual assessment, especially for sources below 5000 Kelvin. Numerically, the highest possible CRI is 100, for a black body, dropping to negative values for some light sources. Low-pressure sodium lighting has negative CRI. Fluorescent light range from about 50 for the basic types, up to about 90 for the best triphosphor type. Typical LEDs have about 80 plus CRI, while some manufacturers claim that their LEDs have achieved up to 98 CRI. A newer version of the CRI, a 96er, has been developed, but it has not replaced the better-known RA General Color Rendering Index. History: researchers use daylight as the benchmark to which to compare color rendering of electric lights. In 1948, Boomer described daylight as the ideal source of illumination for good color rendering because it displays a great variety of colors, makes it easy to distinguish slight shades of color, and the colors of objects around us obviously look natural. Around the middle of the 20th century, color scientists took an interest in assessing the ability of artificial lights to accurately reproduce colors. European researchers attempted to describe illuminance by measuring the spectral power distribution in representative spectral bands, whereas their North American counterparts studied the colorimetric effect of the illuminants on reference objects. The CIE assembled a committee to study the matter and accepted the proposal to use the latter approach, which is the virtue of not needing spectrophotometry, with a set of Munsell samples. 8 samples of varying hue would be alternately lit with 2 illuminants, and the color appearance compared. Since no color appearance model existed at the time, it was decided to base the evaluation on color differences in a suitable color space, CIE-UVW. In 1931, the CIE adopted the first formal system of colorimetry, which is based on the trichromatic nature of the human visual system. CRI is based upon this system of colorimetry. To deal with the problem of having to compare light sources of different correlated color temperatures, the CIE settled on using a reference black body with the same color temperature for lamps with a CCT of under 5000 K, or a phase of CIE standard illuminant D otherwise. This presented a continuous range of color temperatures to choose a reference from. Any chromaticity difference between the source and reference illuminants were to be abridged with a von Kres-type chromatic adaptation transform. Test method: the CRI is calculated by comparing the color rendering of the test source to that of a perfect source, which is a black body radiator for sources with correlated color temperatures under 5000 K, and a phase of daylight otherwise. Chromatic adaptation should be performed so that light quantities are compared. The test method needs only colorimetric, rather than spectrophotometric, information. Using the 2-degree standard observer, find the chromaticity coordinates of the test source in the CIE 1960 color space. Determine the correlated color temperature of the test source by finding the closest point to the Planckian locus on the chromaticity diagram. If the test source has a CCT less than 5000 K, use a black body for reference. Otherwise use CIE standard illuminant D. Both sources should have the same CCT. Ensure that the chromaticity distance of the test source to the Planckian locus is under 5.4 A, 10 or 3 in the CIE 1960 UCS. This ensures the meaningfulness of the result, as the CRI is only defined for light sources that are approximately white. Illuminate the first 8 standard samples, from the 15 listed below, alternately using both sources. Using the 2-degree standard observer, find the coordinates of the light reflected by each sample in the CIE 1964 color space. Chromatically adapt each sample by a von Kres transform. For each sample, calculate the Euclidean distance between the pair of coordinates. Calculate the special CRI using the formula. Find the general CRI by calculating the arithmetic mean of the special CRIs. Note that the last 3 steps are equivalent to finding the mean color difference, and using that to calculate. Chromatic adaptation. CIE uses this von Kres chromatic transform equation to find the corresponding color for each sample. The mixed subscripts refer to the inner product of the test illuminant spectrum and the spectral reflexivity of sample I. Where subscripts A and T refer to reference and test light sources, respectively. Test color samples, as specified in CIE, the original test color samples are taken from an early edition of the Munsell Atlas. The first 8 samples, a subset of the 18 proposed in Nickerson, are relatively low saturated colors and are evenly distributed over the complete range of hues. These 8 samples are employed to calculate the general color rendering index. The last 6 samples provide supplementary information about the color rendering properties of the light source. The first 4 for high saturation, and the last 2 as representatives of well-known objects. The reflectance spectra of these samples may be found in CIE, and their approximate Munsell notations are listed aside. A 96er method. In the CIE's 1991 quadrennial meeting, Technical Committee 1-33 was assembled to work on updating the color rendering method, as a result of which the A96er method was developed. The committee was dissolved in 1999, releasing CIE, but no firm recommendations, partly due to disagreements between researchers and manufacturers. The A96er method has a few distinguishing features: a new set of test color samples, 6 reference illuminants, D65, D50, black bodies of 4200K, 3450K, 2950K, and 2700K, a new chromatic adaptation transform, CIEC 1894. Color difference evaluation in Sciob. Adaptation of all colors to D65. It is conventional to use the original method. A 96A should be explicitly mentioned if used. New test color samples. As discussed in Sander and Zander, CIE recommends the use of a color checker chart owing to the obsolescence of the original samples, of which only mtameric matches remain. In addition to the 8 color chart samples, 2 skin tone samples are defined. Accordingly, the updated general CRI is averaged over 10 samples, not 8 as before. Nevertheless, Hung has determined that the patches in CIE give better correlations for any color difference than the color checker chart, whose samples are not equally distributed in a uniform color space. Example: the CRI can also be theoretically derived from the SPD of the illuminantum samples since physical copies of the original color samples are difficult to find. In this method, care should be taken to use a sampling resolution fine enough to capture spikes in the SPD. The SPDs of the standard test colors are tabulated in 5 nm increments CIE, so it is suggested to use interpolation up to the resolution of the illuminant spectrophotometry. Starting with the SPD, let us verify that the CRI of reference illuminant F4 is 51. The first step is to determine the TRIS stimulus values using the 1931 standard observer. Calculation of the inner product of the SPD with the standard observer's color matching functions yields equals 109.2, 100.0, 38.9. From this follow the XY chromaticity values. The next step is to convert these chromaticities to the CIE 1960 UCS in order to be able to determine the CCT. Examining the CIE 1960 UCS reveals this point to be closest to 2938 K on the Planckian locus, which has a coordinate of. The distance of the test point to the locus is under the limit, so we can continue the procedure, assured of a meaningful result. We can verify the CCT by using Maykam's approximation algorithm to estimate the CCT from the XY chromaticities, where substituting yields n equals 0.4979 and CCT-EST equals 2941 a K, which is close enough. Since 2940 of 5000, we select a Planckian radiator of 2940 a K as the reference illuminant. The next step is to determine the values of the test color samples under each illuminant in the CIEUVW color space. This is done by integrating the product of the CMF with the SPDs of the illuminant and a sample, then converting from CX to CIEUVW. From this we can calculate the color difference between the chromatically adapted samples and those illuminated by the reference. The special CRI is simply. Finally, the general color rendering index is the mean of the special CRIs, 51. Typical values: a reference source, such as blackbody radiation, is defined as having a CRI of 100. This is why incandescent lamps have that rating, as they are, in effect, almost blackbody radiators. The best possible faithfulness to a reference is specified by a CRI of 100. While the very poorest is specified by a CRI below 0. A high CRI by itself does not imply good rendition of color, because the reference itself may have an imbalanced SPD if it has an extreme color temperature. Criticism and resolution: Ono and others have criticized CRI for not always correlating well with subjective color rendering quality in practice, particularly for light sources with spiky emission spectra such as fluorescent lamps or white LEDs. Another problem is that the CRI is discontinuous at 5000 a K, because the chromaticity of the reference moves from the Planckian locus to the CIE daylight locus. Davis and Ono identify several other issues, which they address in their color quality scale. The color space in which the color distance is calculated is obsolete and non-uniform. Use SciLab or SciLuv instead. The chromatic adaptation transform used is inadequate. Use CMCCAT 2000 or CIECAT 02 instead. Calculating the arithmetic mean of the errors diminishes the contribution of any single large deviation. Two light sources with similar CRI may perform significantly differently if one has a particularly low special CRI in a spectral band that is important for the application. Use the root mean squared deviation instead. The metric is not perceptual. All errors are equally weighted, whereas humans favor certain errors over others. A color can be more saturated or less saturated without a change in the numerical value of AE, while in general a saturated color is experienced as being more attractive. A negative CRI is difficult to interpret. Normalize the scale from 0 to 100 using the formula. The CRI cannot be calculated for light sources that do not have a CCT. 8 samples are not enough since manufacturers can optimize the emission spectra of their lamps to reproduce them faithfully, but otherwise perform poorly. Use more samples. The samples are not saturated enough to pose difficulty for reproduction. CRI merely measures the faithfulness of any illuminant to an ideal source with the same CCT, but the ideal source itself may not render colors well if it has an extreme color temperature, due to a lack of energy at either short or long wavelengths. Weight the result by the ratio of the gamut area of the polygon formed by the 15 samples in SciLab for 6500 a K to the gamut area for the test source. 6500 a K is chosen for reference since it has a relatively even distribution of energy over the visible spectrum and hence high gamut area. This normalizes the multiplication factor. Rhee and Friedrich have developed another index, the gamut area index, in an attempt to improve over the flaws found in the CRI. They have shown that the GAI is better than the CRI at predicting color discrimination on standardized Farnsworth-Munsell 100 hue tests and that GAI is predictive of color saturation. Proponents of using GAI claim that, when used in conjunction with CRI, this method of evaluating color rendering is preferred by test subjects over light sources that have high values of only one measure. Researchers recommend a lower and an upper limit to GAI. Use of LED technology has called for a new way to evaluate color rendering because of the unique spectrum of light created by these technologies. Preliminary tests have shown that the combination of GAI and CRI used together is a preferred method for evaluating color rendering. Poussett, Urbane and Razet developed a psychophysical experiment in order to evaluate light quality of LED lightings. It is based on colored samples used in the color quality scale. Predictions of the CQS and results from visual measurements were compared. CIE reviews the applicability of the CIE color rendering index to white LED light sources based on the results of visual experiments. Chaired by Davis, CIETC 1-69, C, is currently investigating new methods for assessing the color rendition properties of white light sources used for illumination, including solid-state light sources, with the goal of recommending new assessment procedures. By March 2010. For a comprehensive review of alternative color rendering indexes, see Guo and Hauser. Smith reviewed several alternative quality metrics and compared their performance based on visual data obtained in 9 psychophysical experiments. It was found that a geometric mean of the GAI index and the CIE-RA correlated best with naturalness, while a color quality metric based on memory colors correlated best for preference. The differences in performance of these metrics with the other tested metrics. CSA. Judd Flattery. Thornton CPI. MCRI, were found to be statistically significant with p less than 0.0001. Dangle et al. Performed psychophysical experiments and concluded that Fiopli unregistered trademark S judgments of naturalness and overall preference could not be predicted with a single measure, but required the joint use of a fidelity-based measure and a gamut-based measure. They carried out further experiments in real offices evaluating various spectra generated for combination existing and proposed color rendering metrics. Film and video high CRI LED lighting incompatibility. Problems have been encountered attempting to use otherwise high CRI LED lighting on film and video sets. The color spectra of LED lighting primary colors does not match the expected color wavelength band passes of film emulsions and digital sensors. As a result, color rendition can be completely unpredictable in optical prints, transfers to digital media from film, and video camera recordings. This phenomenon with respect to motion picture film has been documented in an LED lighting evaluation series of tests produced by the Academy of Motion Picture Arts and Sciences scientific staff. To that end, various other metrics such as the TLCI have been developed to replace the human observer with a camera observer. Similar to the CRI, the metric measures quality of a light source as it would appear on camera on a scale from 0 to 100. There are some manufacturers that claim TLCI values of up to 99. References. Sources: CIE, Color Rendering, Publication 135/2, Vienna, CIE Central Bureau, ISBN A3-900734-97-6. CIE, CIE Colorimetric and Color Rendering Tables, Disc D002, Rel 1.3. CIE, Color Rendering of White LED Light Sources, Publication 177/2007, Vienna, CIE Central Bureau, ISBN A978-3-900-1906-57-2A. Carried out by TC 1-69, Color Rendering of White Light Sources. Barnes, Bentley T., Band Systems for Appraisal of Color Rendition, JOSA 47, 1124/1129, doi, 10.1364/JOSA. 47.001124, Bodrigi, Peter, Color Rendering, Past, Present, 2004, and Future, CIE Expert Symposium on LED Light Sources, PPA 10/12. Crawford, Brian Hewson, Measurement of Color Rendering Tolerances, JOSA 49, 1147/1156, doi, 10.1364/JOSA. 49.001147. Davis, Wendy. Ono, Yoshi, Color Rendering of Light Sources, Nista, Hung, Po Chai, Sensitivity Mtamerism Index Digital Still Camera, Indizantsor, Mingoleo, Kiaruazora, Color Science and Imaging Technologies, Proceedings of SPIE 4922, PPA 1 Euro 14, doi, 10.1117/12.483116. Nickerson, Dorothy, Light Sources and Color Rendering, JOSA 50, 57 Euro 69, doi, 10.1364/JOSA 50.000057. Ono, Yoshi, 5th Symposium Optics in Industry, in E. Rosas, R. Cardoso, J. C. Bermudez, O. Barboza Garcia, Proceedings of SPIE 6046, PPA 604625 Euro 1 Euro 604625 Euro 8, doi, 10.1117/12.674617. Poussett, Nicholas. Urbane, Gail. Razet, Anik, Visual Experiment on LED Lighting Quality with Color Quality Scale Colored Samples, Proceedings of CIE 2010. Lighting Quality and Energy Efficiency, Vienna, Austria, 722 Euro 729. Zhander, Janos, The Concept of Color Rendering Revisited, First European Conference on Color in Graphics Imaging and Vision, Poitiers, France. Thornton, William A., Color Rendering Capability of Commercial Lamps, Applied Optics 11, 1078 Euro 1086, doi, 10.1364/AO. 11.001078. Smith, K.A.G., Correlation between Color Quality Metric Predictions and Visual Appreciation of Light Sources, Optics Express 19, 8151 Euro 8166, doi, 10.1364/A. 19.008151. Dangle, R. Islam, M. Hiva Currency Rinan, M. Uzel, P. Ualaka, M. Halonen, L. Subjective Preferences and Color Quality Metrics of LED Light Sources, Lighting Research and Technology 45, 666 Euro 688, doi, 10.1177/1477153512471520, ISNA 1477-1535. Islam, M.S. Dangle, R. Hiva Currency Rinan, M. Uzel, P. Ualaka, M. Halonen, L. User Preferences for LED Lighting in Terms of Light Spectrum, Lighting Research and Technology 45, 641 Euro 665, doi, 10.1177/1477153513475913, ISNA 1477-1535. External links, MATLAB script for calculating measures of light source color, Rensselaer Polytechnic Institute, 2004. Excel spreadsheet with a cornucopia of data, Lighting Laboratory of the Helsinki University of Technology, Uncertainty Evaluation for Measurement of LED Color, Metrologia, Color Rendering Index of Common Light Source, Color Rendering Index and LEDs, United States Department of Energy, Office of Energy Efficiency and Renewable Energy, Bad Link, Alliance for Solid-State Illumination Systems and Technologies, Color Rendering.